Can you guys see the screen? Okay. Is it too bright here? Okay, whatever. Okay, let's get started. So today we will talk about CPU architectures and also assembly languages. We will take a close look at two architectures, actually this week, not just today, x86, and which is 32-bit, and also x86 64-bit. And we will also look at their instruction sets. So both architectures, they are what we call complex instruction set architecture, or CIS. Then I will also show you guys some examples of a different design philosophy of CPU, especially their instruction set, which is called the reduced instruction set computers, or RISC. So most of your laptops, PCs you are using, you are still using Intel CPU. So most Intel CPUs are still a CISC architecture, but your phone, tablet, if you are using M1, M2, then you are using an ARM CPU, and ARM CPU use a RISC architecture. So the Intel CPU actually, under the hood, now they are also switching to a RISC architecture. So Intel was the very first, among the very first vendors of CPUs, and they designed everything using this complex instruction set philosophy. Then some professors from Berkeley, they came up with the idea of RISC, and actually they also got Turing Award for that. And also, last Friday, we released assignment 1. So today I will try to give you maybe 30 or 20 minutes in the class to finish assignment 1, and I will walk around to help you guys there. Okay, so I will first give you an overview before we dive into the CPU architecture, give an overview of a computer organization, right? So a computer is made up of many different components. There are CPUs, main memory, or usually they are called RAM, GPU, storage, microphone, camera, all of them combined together, they are your personal computer. So they are all connected to something we call the motherboard. There are many slots on the motherboard. You plug in different components. And the motherboard, they have buses that link the components together. So different components, they can communicate and they can work together as a system. So last week, we talked a little bit about North Bridge, South Bridge. There are different buses on the motherboard. North Bridge usually is faster for high performance devices than South Bridge for other USB much slower, disk much slower devices. So then what is computer architecture? So computer architecture, we don't really have the class in our college, but I think the EE offers such a class. So this discipline is about the design and the organization of a processor, okay? So computer architecture is not really about the organization of your whole personal computer. It's mainly about the processor itself. And there are many different types of processors. CPU is usually the example we use in this class. And the GPU is another very popular processor, especially GPU, general purpose GPU. They are widely used in machine learning, deep learning, large language models right now. So computer architecture studies the design of those processors. And those processors, they execute something we call instructions. They expose some API we call instructions. So software will issue instructions to those processors, GPUs or CPUs. Then the processors will try to do some computation, handle some data, and also interact with other devices on your personal computer or data center computer, whatever. So instructions are basically binary encoded operations the processors can understand. The instructions are commands you are issuing as a software developer, you issuing to the CPUs. So you tell the CPU what actions to perform, and we have many different instructions for one CPU or one GPU, and they form a set. We call them instruction set architecture. So basically, that's the interface between hardware and software. So hardware, CPU, GPU, they provide an interface to the software, which are the instructions. And you do not need to understand internally the inner working of CPU or GPU. You only need to understand the interface, how to use them. The assembly language, they are human readable representations of those machine instructions. So they are not those binary encoding of those instructions. They are a human readable text version of those instructions, which you can easily read. Human can read, but machine cannot understand that. For machine to understand, we need an assembler to translate the human readable text into those instructions. So last week, I talked about how each layer in a computer provides services to the upper layers, right? Through some well-defined interface. So for CPU and hardware, GPU processors, the interface they provide is called instructions. On top of instructions, we develop software. The software can be operating system, which will be the core of this class. Then the operating systems, they are software. Software is made up of a sequence of instructions. So on modern Linux, we're talking about maybe 15 million of instructions. Also maybe 10 million, 20 million of sequence. On top of the operating system, we can run different applications. And most of applications, if they are native applications, they are also made up of instructions. So both the applications and the OS, they are actually made up CPU instructions. They just run in different mode. The OS run in the privileged mode, and applications run in unprivileged mode. And we have virtualization to separate different applications. So if one application crash, it will not crash your whole computer. And the OS also provides some kind of interface to the applications, and that is called system calls. Of course, there are other standards. For example, the POSIX interface standard, they do not only define system call interface, they also define other interfaces. So later we will say system calls, they are actually also implemented in some special instructions. So you can think CPU and the main memory or RAM as the two most essential parts of a modern computer. The CPU is the brain. It does all the thinking, computation, and the RAM holds the code and the data the CPU is working on. So without them, we basically do not have a computer. So the key here is both code and data. The code are just the instructions. Both code and data, they are stored in memory. They're not stored in CPU. So when CPU wants to execute some code, the CPU needs to fetch the code from the memory, then decode that instruction and execute that. And that instruction may also require some other data. So the CPU will also fetch the data from the main memory to the CPU. The CPU has its own storage. Those are called the registers. However, relatively, this part is very small. They are very fast. So CPU is on one die. The memory is on another component. They're not on the same die. So registers usually are very small compared to memories. Memory, we're talking about your laptop, probably at least 8 GB now. So some of you, your laptop maybe 32 gigabytes, but the registers are very small. So we're talking about 32 bits, 4 bytes, 64 bits, or some floating registers could be 128 bits, 512 bits, but still, compared to the main memory, it's very small, right? So when CPU fetches some code from memory, so how does the CPU fetch something? How do you indicate what I want to fetch, or even fetch some data? How do I indicate that? How does CPU tells the memory I want to fetch this, not that, right? So CPU use something called the memory address to do that. CPU tells the main RAM the bytes at this memory address is what I want to fetch. I may fetch the code, I may fetch the data. Okay. So the addresses, they are just indexed into this main memory. So because the CPU needs to give the memory the address, especially for instructions, then we have a special register in general that is called program counter, PC. And different architectures have different specific name for this register. The architecture we're gonna look at today, call it IP, instruction pointer, or EIP. So in general, you just call it PC, program counter. So this register always holds the next instruction, the address of the next instruction to be executed. Okay. Then we also have some other registers to store the status of the program or the status of the CPU. There are many special registers for that. Okay, so from assembly programmer's point of view, what we can do with the CPUs. CPUs basically provides several classes of instructions, and software uses those instructions. There are instructions to move data between memory and the registers. You can move the data from main memory to CPU to main memory register. You can move data from a register to another register. You can move data from the register to the main memory. So data movement. There are different instructions to perform all kinds of computations, arithmetic or logical operations. And most of those operations are on registers. Some of the instructions can also perform on register and memory, okay? So obviously, if the operation is only in the register, it will be very fast because the operation doesn't need to go out of the CPU. Some of the operations you need to fetch the memory, then even write back to the memory, that will be much slower. Okay. Then the third class of instructions are just the control flow transfer instructions or transfer control instructions. There are jumps, there are branches. So you already program in Java or Python already. So you have if statement, you have while statement. So for those statements, you do not necessarily go to the next instruction. There is some kind of a predicate, some kind of a comparison. Depending on the result of the predicate, the program will decide what to execute next, right? So at the hardware CPU level, we also have those instructions. So your predicate eventually compiled into those kind of instructions. Jumps, branches, some of the jumps could be, we call in program analysis, we call direct jump, means the target of the jump is decided at compile time. And some of the jump could be called indirect jump, means the target, the destination is not decided at compile time. Only runtime, you will figure out what's the target. So that's basically what the CPU provides, those three classes of instructions. And all the magics of the CPU really boils down to those types of very simple operations. So all the fancy things you are saying on computers, eventually those are just those three classes of operations. As simple as that. So if we know how to program in assembly, then you can take full control of the CPU. So this is kind of like driving a stick, right? So you are directly in charge of everything. If you program in high-level language, even if you program in C, then the language can abstract away a lot of details. If you program in Python or Java, then it's totally different because they run on top of a virtual machine. And that virtual machine eventually maps down to the physical machine. So there are multiple layers of translation. The benefit of doing that is it's easier to program in Python and Java, right? It's much easier to program in JavaScript. You cannot make many mistakes in JavaScript, syntax mistakes. But at assembly level, you make all kinds of mistakes. And one single mistake will crash the whole thing. It's very difficult to program in assembly. However, it can be very, very efficient. Program in Java, JavaScript, Python can be much easier. It's more friendly for beginners. However, because multiple layers of translation, the program will run very slow. So if we record the C tool chain I showed you last week, we have C code, we go to this .I code, eventually we go to the assembly. The assembly, so we do not directly compile C code to machine code. We always compile them to assembly. They use assembler to compile to the machine code. So this step from assembly to machine code is quite easy because it's just one is binary presentation, another one is the human readable representation of the almost the same thing. And last week, I also showed you that from those binary files, like .o file or executable files, there are some sections in those files, they are just the code. They are just the instructions. So what if we want to read those instructions? We want to know what instructions are those, right? So if we open a file, we can see just raw bytes. So if we understand what instructions are those raw bytes, we can use tools like objdump. To use this tool, we can get something we call a disassembly. So this is not the assembly we had before, right? This is different from the assembly, but they are similar. They have all those instructions in human readable representations. So if we look back the history of programming languages, it all started with just the machine code. Early software developers in the 1940s and 50s, they directly code in machine code, which is very difficult. Then many assembly languages were developed, which just a human readable presentation of the same machine code. If you look at the early assembly languages developed in the 50s, we have many assemblers. So those are relatively simple. They translate the equivalent human readable format to the machine binary format. And the C programming language was only developed in the 70s. And after 50 years, we are still using it. We are still using it in all kinds of systems. So I believe the inventors of C also got Turing Award for inventing C and Unix at the same time, I believe. So even modern days, assembly is still relevant. Like I said before, the benefit of programming in assembly is it can be super fast. It's very difficult to program, but super fast. So for scenarios that we need absolute speed, or we want the code to be very small, we can still program in assembly. So today I'm going to show you a little bit code of the XV6 kernel, which is in assembly. For that piece of code, actually, we have to use assembly because that's at the very beginning of the PC boots. You do not have the stack set up. You do not have the interrupt set up. So you cannot use C yet. Then we still have, let's say, I mentioned about this game, Roller Coaster Tycoon 2. So this is a game I've been playing for maybe 20 years. And this is totally developed in x86 assembly, which is crazy. It's a ton of work put into that. Understanding assembly will also help you to understand how CPU works, which will help you debug what the problem box really is. Even if you spend most of your time writing in high-level languages like Python or Java. Learning assembly is also very helpful. For example, Java and Python, they both run on their own virtual machines. And that virtual machine is not a real CPU, but the design of virtual machine is similar to the design of a real physical CPU. So they have their own instructions. So your Java code eventually will be compiled into something like this. So those are still instructions. For example, here we have a load, we have a new, we have a stop, to duplicate something. This is a new command. This is invoke special. So this is kind of a call instruction. You're calling some functions, right? So the design philosophy for those virtual machines are also very similar to physical CPUs. Python, the same thing. So even if Python do not necessarily need to be compiled, it can be interpreted. Let's say here we have calling a function, and this function eventually will be interpreted into those instructions. We're loading something, we're loading a const, compare two things, pop something, call a function, right? So those are basic commands at the virtual machine level of Java and Python, and they will be very similar to our physical CPUs later. So today we will skip the C part. We will talk about the C 2 weeks later, mainly focus on the assembly part. But I will still want you to know that because of the layers of abstraction, when you program in C or assembly or Java, you worry about different things. At assembly level, you do not really have the concept of variables, which you are familiar with. You do not necessarily strictly have the concept of function. There are procedures similar, but not necessarily all the same. At the assembly level, you need to think like how the CPU works. So you are facing different memory addresses. At different memory addresses, you have different bytes. And there are no semantics associated with that. And you, as a programmer, you need to know what is what. You also need to know how to control the registers. For which register you want to do what. For some registers, you want to do computation. For some registers, they have special purposes. You need to understand that. But of course, you do not need to understand what a hardware engineers or a CPU designers, they need to understand, right? They need to worry about the microarchitecture level, the inner working of CPUs. You don't need to understand that. You only need to understand the instructions. So that's what we are going to look at today. So in this class, we mainly use the Intel x86 instruction set as the example, because it's still the very popular CPU, even though Intel stock price has been dropping. NVIDIA is stock price is going up, and they design GPU, and ARM is another very popular designer of CPUs, and the RISC-V is another very strong competitor. But most of our data centers, we're still using Intel. So the Intel x86 instruction set or the follow-up 64-bit version of that, they are not only designed by Intel. The earlier version was designed, 32-bit version was designed by Intel, and Intel struggled a little bit to expand to the 64-bit version. Then AMD was actually the first one to really design a 64-bit version by extending the 32-bit version of the Intel architecture. So a little bit comparison between a complex instruction set computer and a reduced instruction set computer. So you will say soon, some of the instructions on Intel architecture can be very long, can be very complicated. They can do operations that you feel you can divide them into multiple operations. That's why they are called complex instructions. One instruction can do some complex things. Then in reduced instruction set, each instruction, all the instructions are relatively simple. They will do simpler things. They're not going to do something very complicated. So if at the C code level, high programming language level, you do something very complicated, then for a complex instruction computer, the compiler can compile that very complicated C statement into 1 or 2 instructions. But it needs to compile to many, many more instructions for reduced instruction set computers. The benefit of this is for CISC computers, developing a compiler for it will be much easier. However, developing a compiler for a RISC CPU will be a little bit harder. And at the early stage of compiler development, it was very challenging. However, then for a CISC computer inside the CPU, because the instructions can be very complicated, they need much more physical space for the decoders and the execution modules. So you need more physical resources on the CPU for that. For the RISC architectures, everything is simple. You can save more space for make the CPU much smaller, physically smaller, and the design can be. When you make the CPU smaller, the energy cost will also be lower. The temperature for the CPU will also be lower. So there are many benefits of that. That's why we say a lot of mobile devices we're using RISC architectures. All your phones are using RISC architecture. We do not say any phone using CISC architecture. But like I said, under the hood now, even Intel CPUs under the hood using a RISC architecture, but that's not a part of this class. So next we will talk about the x86 architecture. So Intel released a lot of processors in the late 70s, 80s, and the very first one is called 8086 or 8088. I think 8086 was the very first one, right? Then they have multiple CPUs coming out that around that time, 8186, 8286, 8386 in 1984. So 8386 was a very, very important one. It added the memory paging here, and 8286 added protected mode. That's all the programs we are running right now in protected mode. And before that, they only have something now we call real mode. So later we are going to see some assembly code switching from real mode to protected mode. Let's see. So we do not really have 8586. Now after that we have a Pentium. So that's like one of my very first computers. I was using a Pentium that time. So you can see the early versions, they always start with 80, then something 86. That's why we call this series of CPUs and the instruction set x86. And this is still the instruction set we are using today because the computers you are using today are still backward compatible with the software 40 years ago. So technically you can still run software if those software were developed for Intel. Technically you can still run those 40-old software on modern CPUs. So on this Intel architecture, we first need to remember how big data is on this architecture. Obviously, 1 byte is 8 bits. That's the same everywhere, almost everywhere. Then a word is 2 bytes or 16 bits. That's called a word. Then double word are 4 bytes, 32 bits. Quad words, 64 bits. Double quad word, 8 bytes. Those are for integers. We also have 2 different data types for float numbers or doubles. One is called single precision 32-bit, a double precision 64-bit. We actually have more complicated data types now. So if we map them to C, in C we have a character which is char. Char is just 1 byte, so that maps to a byte. Short maps to a word. Integer int maps to double word, 4 bytes. Long usually is 8 bytes. char star, the star here means this is a pointer, okay? So char star means this is a pointer, points to one character, okay? What is a pointer? Pointer is just an address, it's a memory address. Okay. So char star itself can be a variable type, and so for that variable, its type is char star, and it's an address, okay? And for 32-bit machine, the address is 32-bit. For 64-bit machine, an address is 64-bit. So the char star here, the size could be 8 bytes for a 64-bit machine. But what it points to is just 1 byte because it's character. There are float and doubles. So those how we map C data types to assembly or to the Intel data types. Also, you need to know what is endianness. So endianness is about the ordering of bytes of a value in computer memory or in transmission. We have two popular endianness types. One is called little endian, and another one is called big endian. But in history, there are other ways to order bytes. Let me use this as an example. We have an integer. The integer has 4 bytes. In a little endian architecture like Intel ARM, most of our devices we're using right now use little endian. We're going to store the least significant byte of that value at the lowest address. Okay, least significant byte at the lowest address. Let's say this is a little endian machine. This is a memory. The memory address is 0, 1, 2, and 3. Each address has 1 byte. Okay. Then address 0 is obviously the lower address. Okay. Then for a little endian machine, the 4 bytes, they represent one number, one integer. Then at the lower address 0, this byte, 12 in hex, it's actually the least significant byte for that value, which means the value here, what we get is 78, 56, 34, 12 in hex. So this is the highest, most significant byte. This is the least significant byte. Okay, so this is, so just to remember, least significant byte has the lowest address in a little endian machine. Then for big endian machine, so we don't really have many big endian machine anymore. ARM used to use big endian, but now it's switching to little endian. Mix probably is still using big endian, but I'm not sure if we have any class using mix anymore. But the network transmission we are using, usually they are using a big endian. So in big endian, let's say we have the same thing, address 0, 1, 2, 3. Now the most significant byte will have the lowest address. In this case, 12 is the most significant byte. So this is for one value, for integer or different types. So for the Intel 32-bit architecture, we only have 6 general purpose registers. Each of them is 32-bit, only 6. There are 2 more special and kind of general registers, and there are many special purpose registers to keep track of the state of the CPU and the program. Then there is one 32-bit E-flags register, so flags extension. So the early version, 16-bit version is called flags. 32-bit, they change it to E-flag, extending that to 32-bit. Then there is one program counter. We call it extended instruction pointer register, or EIP. So those are the main registers on this architecture. So you kind of need to remember those names, but they are very easy to remember anyway. So we have EAX, E means extended. Then we have A, B, C, D, EAX, EBX, ECX, EDX. Okay, so those are general registers. ESI, EDI, those are also general registers. So those 6 are general registers. So you can use most cases you can use those registers interchangeably. Okay. However, at the physical level, circuit level, they may be wired differently. For example, if you want to do addition, if you use register EAX, it may be a little bit faster than ECX. That's possible. So that's why if you design a compiler, compile from C code to binary, you may want to consider those kind of constraints, right? Some register may be a little bit faster than other registers, but that's not the core of this class. So how do you remember those registers? We have A, B, C, D. Then we have S, I was source index. D is destination index. Okay, so the 60-bit version of those registers. So this everything here is 32-bit. So they are 82, 86 in the early 80s. Then before that, we only have 16-bit of the Intel CPU. So we do not really have the full EAX. We only have those AX, BX, CX, DX. So they are the lower 16-bit of the same register. Okay. And they have different names. And we can even refer their lower 8-bit as AL, BL, CL, DL. So this is just 1 byte, 8-bit, right? Then we can also refer to the higher 8-bit. Then ESI, DSI, you can refer the lower 16-bit, but you cannot really refer the lower 1-bit to that. Then we have 2 more registers, kind of special, ESP and EBP. They are for stack pointers and base pointers. Today, we're not going to talk about that. So they are very important for hacking in my software vulnerability and security class. So we spend many weeks thinking about how to manipulate those registers in that class to hijack programs. Then we have flag registers, also E-flag registers, also 32-bit. So there are several useful bits in this register. We are not using full 32-bit, and those bits are indicators of the result of a previous operation. Let's say you want to add 2 numbers together, and that addition overflows. Then we need to indicate there is an overflow. So there is a bit in that register for the carry flag. Just 1 bit, 1 means there was an overflow. Then if you want to subtract a number from another number, and the result is 0, then there is a 0 flag to indicate the result is 0. There are several other flags, including sign flags. So those are in the E flag register. And the program counter or the instruction pointer, 32-bit, it is 32-bit because this is a pointer. This is the same concept of the C programming language level pointer. Pointer is an address. And for a 32-bit machine, the address is 32-bit. Okay, which means the memory can only be 4 gigabytes. 2 to the power of 32, that's 4 gigabytes. Then this register always holds the address of the next instruction the CPU is about to execute. And that address is a memory address. There is no such concept inside the CPU of address. Inside CPU, there are registers. All those storage, they have a name inside CPU. Those names are the register name, EAX, ECX. For memory, then we only have address for each byte. We don't really have a name for it. So how the CPU works, we have general registers. We already saw that. EAX, EBX, ECX, EDX. We have those condition code, the E flags. We have the program counter, the EIP. So when you execute a program, the program is made up of instructions, a sequence of instructions. Each instruction does a particular operation. So the CPU has the program counter. It has an address. From that address, it's going to find that instruction. It's going to, and this is a memory, it's going to fetch that instruction from the memory to the CPU, decode that, because those are just raw bytes, decode that, figure out what this operation is, and try to perform that operation. And that operation may also need some data, work on other memory addresses. The CPU needs to fetch that data from the memory to the CPU again. Maybe it needs to put them into the registers. Then eventually, after the operation, the CPU may put things back to the memory. Okay. So that's why you can say this is actually a very slow procedure. The CPU needs to talk to the memory. There are two different components on the motherboard. That's why a lot of optimization is going on in computer architecture to make things faster. So we can add layers of caches here. Okay. So by fetching something from the memory, we also store a copy of that thing in the CPU instead of always we need to fetch from the memory. We store it here and we do computation here. After the computation, if we decide to put it back to memory, we can put it back to memory, or otherwise it just stay here. So if you look at modern CPU, much of the die area is reserved for caches. Most of the areas are actually reserved for caches to make things much faster. So also in this class, we are going to look at two different addresses. One is a physical address a little bit. That's the physical address of memory and also virtual memory. So most of the programs, I guess since most of you are developing applications so far, you haven't developed any kernel modules or whatever. So your programs, they run in something called a virtual address space. And it is the OS to create that kind of a virtual memory illusion for each application. So what you are looking at, what you're debugging, we're actually in the virtual address, not physical address. Today, we're going to look at a small piece of code which use a little bit of physical address there. So virtualizing memory is one of the most important jobs of the operating system. So here we have a full overview of the registers on a 32-bit x86 machine. So this one actually has 32-bit and also 64-bit. So this figure is actually very interesting. There are some registers we already saw before, like EAX, EBX, ECX, EDX, EBP, ESP, EDI, ESI, right? Those 6 general purpose registers and 2 more stack-related registers. Okay. So for 32-bit version, we have the EBX, or starting with. Then moving to the 64-bit version, which came out maybe 15, 20 years ago, so we extend the 32-bit register EAX into RAX. Okay. So now we have RAX, RBX, RCX, RDX, and you can still refer to the lower 32-bit as EBX or EAX. Then we also have some new registers from R8, R9 to R15. So those are new registers. They didn't exist for the 32-bit version, but they are new in the 64-bit version. So the 64-bit version of the CPU, not only the registers are bigger, there are more general purpose registers. Okay. So EIP, the program counter, also becomes the RIP. Then we have many configuration registers, CR. So those are very important if you program the operating system. If you program at application level, you will never touch those registers. Even if you program in C, your program will be compiled into instructions, right? Those instructions, if you are programming an application, those instructions will never directly touch those registers. Okay. Those are configuration registers our operating system were used. Several of them are very important. We're going to study them in this class. One is the CR0, configuration register 0. It will determine the mode of the CPU, whether it's real mode or protected mode. So remember we talked several minutes ago, 80 to 86 introduced something called the protected mode, introduced the pages. So before that, there is no memory virtualization. Then CR3 is the register to store the physical address of your memory page tables, which we will study in the module of process. So each process has their own edition of virtual memory. They think they have 4 GB of memory, but actually your computer may only have 1 GB of physical memory, right? Then there is something called page table to tell the CPU how to translate a virtual address into a physical address. And that page table is also stored in the main memory. And the address of that page table is stored at this register CR3. So for different process, each of them will have their own CR3 value. When this application is running, the OS will swap in that application's CR3 value into the register. Otherwise, they can store that in memory. Then we have some debug registers here, those for debugging. We have many of those registers. Then we have, this is called the segment registers. They have been there since the very beginning of Intel CPU. CS is code segment. SS is probably stack segment. ES is data segment. ES probably extra segment. I don't remember what they are for the name anymore. So anyway, we're not really using segmentations anymore in modern CPUs or modern operating systems. Only earlier ones were using segmentations. So those registers are still useful nowadays, but they are used for different purposes, not used for segmentation anymore. Then we have a global description table register, interrupt description table register. Those are also for OS to use. Then we have E flags extending to R flags. So that is the general registers, configuration registers, debug registers, and we can call this part of the system registers, very important system registers. So this side, we have some multimedia registers. So this probably I think this were introduced in the early 2000s. I still remember when I have my very first computers, all the advertisement of Intel was about all those kind of multimedia registers. I think MM here means multimedia, and now they are much bigger. So this is probably 512 bits of register. But still, compared to GPUs, with those multimedia registers, the number of them are still very small compared to what we have on GPUs. Any questions so far? We're good? Okay, now we're going to learn those Intel x86 instructions. So each instruction, first of all, has a name. We can call it an operation, we can call it mnemonic. It's basically a name, okay? It tells us what instruction it is, and that instruction may have different numbers of operands. They're like parameters, the different numbers of parameters. So Intel CPU x86, the operand could be up to 3 or 4, I believe. And some of the instructions doesn't have an operand. They do not take parameters. Some of them take 3 parameters. And we're going to use AT&T syntax in this class because the code we're looking at, x86, use AT&T syntax for assembly. And for my software security class, we actually use Intel syntax. I like Intel syntax much more. Anyway, then for each instruction, or this could be a assembly statement, right? And that eventually maps to one instruction. A C statement do not necessarily map to one instruction, can map to multiple instructions. But an assembly statement usually map to one instruction. And you can have a label for that. So basically you give a name to that instruction at this particular address. So this label eventually just become an address. It's at runtime, what is the address for that? Okay, that's it. Then each operand can be a number or we call it an immediate value. That's just a number. It can be a name of a register. It can also be a memory address. Those are the possible values for an operand. Then in the AT&T syntax, we have the previous one. The AT&T syntax, the first operand is the source. The second operand is the destination. Okay, you need to remember that because for the Intel syntax, it's the opposite. For many other architectures, if you work on ARM or MIPS, you will see the first operand is actually the destination. The second is the source. But for the AT&T syntax, it's opposite. So let's see some concrete examples. The first example is HLT. This instruction basically holds the CPU, puts the CPU into sleep mode. Okay. So the purpose of doing this is to save energy. For many embedded systems, the device may be deployed in field for 10 years, 20 years, without power supply. They may be running on some battery. Then when there is no program to run, you want to put the CPU in sleep. Then you can have an instruction force to do that. And the CPU will resume execution if there is some external events. And those will trigger some interrupt to restart or resume the CPU. So this instruction, obviously, you don't really need any parameter, right? So that's why this is just an instruction. There's no parameter. Then this instruction, INC, means increment. You just add one to a register, or you can also add one to a memory address. That's it. So the parameter for that, the operand for that is just a register name or memory address. That's it. Then if we want to add two values together, those two values could be registers. Then you can use an add instruction. And this one takes two operands. The first one is the destination. The second one is the source. No, sorry. The first one is the source. The second one is the destination. So what you do is you add the value of in the first register to the value in the second register and store the result in the second register. And the first register value doesn't change. Okay. So you can see this is a instruction using two operands. For this one, integer multiply, IMUL, integer multiply. It can take three registers. We have a register, another register, and we have a constant. We can multiply the constant with a register, then put the value in another register. So the key to remember here is in this syntax, Intel. Oh, so sorry, this is Intel. Let me skip this one. Need to update that. Okay. So registers. There can be those general registers we already talked about. There are 8 of them. 2 of them are actually kind of special. ESP, S is a stack. B is base. ESP, EBP are kind of special. Compilers will use them for special purposes. Compilers usually use them to construct the stack, which we will talk about next class. And we'll talk about that a lot in my hacking class. Then we actually only have 6 general registers here, right? A, B, C, D, E, and SI and VI. So you can use 32-bit version of those registers. You can use 16-bit version and also 8-bit version of those registers. The memory address, the syntax here is in AT&T syntax. You need to put the register name or a number inside parentheses. Okay. So if you see a pair of parentheses like this, it means we are not referring to the register itself. Instead, we are referring to a memory. Okay. And the memory has an address. Right? The address is in the register. So here we are referring to the memory, and the memory's location is in the register EAX. So the content in the register EAX is actually the memory address for what we want to access. So let's see several examples. The first one is a move instruction. One of the most important class of instructions. Move data around, right? So the instruction here is move, M-O-V. There is a L here at the end, means this is, we are moving something 4 bytes, that's it. So there is move B, move L, and move, most likely we're going to use move L, which is 4 bytes. So here what we're doing is, all the register in this assembly language, all the register names, you have to have a prefix percentage sign. Percentage sign means this is a register name, okay? So this one we're moving value in EAX to the register EBX, okay? Move contents in EAX to EBX. So the word move here is actually a little bit confusing, right? You're not really moving, you're duplicating, you're copying something from EAX to EBX. EAX doesn't change after this. You're just copying, but the instruction is called move. So the key here is the prefix percentage sign. When you say percentage sign, then you know it has to be followed by a register name in the syntax. If you want to use some constant or immediate value, you have to use a dollar sign. If you want to load the value 5 into register EAX, you can use the instruction like this. Move L $5 EAX. Okay, so this is moving the value 5 into the register EAX. There is a percentage sign, so you know this is a register. There is a dollar sign, so you know this is a number. Then, so those two instructions, those 3 instructions, we're not going to use the memory. Everything happens in the CPU, and it will be super fast. In modern computers, those operations are almost free, super fast. Okay. So even this one, you're moving a hard-coded value, a constant, to a register. And this hard-coded value is not stored in the memory. It's embedded in the instruction itself. Then, if you want to do some memory operations, like this one, first of all, this is a little bit complicated. First of all, this is a move instruction. So we are going to copy some data from some place to another place. The first operand looks like this. The second operand, we know it's percentage, so it's a register. So we know the destination is EAX. We're moving something to the register EAX. But what we are moving, so you see parentheses here, a pair of them, it means we're moving from the main memory, okay? We're not moving from another register. And for the main memory, where is the address? Where is the location? So the location is stored at the register EBP, which is a base register, and plus some, we call it, let me just call it offset, right? So this is a positive offset 8, which means the address, the memory address is EBP plus 8. We're going to load something from the main memory and the address EBP plus 8 to the register EAX. Moving something from memory to the register. So actually I put another syntax here. This is the Intel syntax. If you compare this one and this one, you will feel this is much easier to understand. This is much clearer, right? But they're the same thing. After all, they compile into binary. Several more examples. Move, parentheses, percentage sign, EBX. So from here, we know we're moving from a memory location. The address of that is in register EBX. We're moving the value at that memory location to a register EAX. Another one, -4, parentheses, percentage sign ESI. So the base address here is the register ESI, and we're moving something from the address ESI -4 to the register EAX. This one is even more complicated. We're moving CL. CL is part of ECX, right? It's also part of CX. So L here means low. So this is actually the register here is only 8 bytes, 8 bits, 1 byte. This is the lowest 8 bits of the register ECX. Okay. Let me go back to that figure so you can see that. So this figure here, let's say the whole 64-bit version is called RCX, 32-bit version ECX, 16-bit version CX, and the lowest 8-bit is called CL. That's a register. So we are moving the 8 bits in CL to some memory location, okay, to the memory, and the address is at ESI plus EAX times 1. Okay, this is a little bit weird. So the reason we are doing this is ESI here is more like the base address. Imagine you are putting something into an array. The array has a base address, right? Now, how do you index array? How do you get each item in an array? There are indexed. Then you don't know the size of each item in that array, right? So the 1 here is hard-coded. So this is the size of the item in that array. Here is 1 byte, and the EAX can be the indexed, starting from 0 to some bigger number. So this instruction, if we add a loop, wrap this instruction, then we can move something to an array, right? So that's how high-level language, a movement to an array, a for statement can eventually compare to something like this. So this is actually the Intel syntax of this with some brackets that will be like that. So it will be ESI plus EX times 1. So Intel syntax clearly shows you what this is doing, but the AT&T syntax doesn't. But they're the same thing. So the next one, we are moving something from memory to the register EDX, and the address is at ESI plus, here is a plus, EBX times 4. Okay, in this case, maybe we are loading something from an array in the memory, and each item is 4 bytes there. Okay, we'll try to load each of them into the register EDX, do some operation. Any questions so far? Yes, in this syntax, you have to have 3 of those. And this is base, index, and size. Yeah. Yeah. Okay. For the investor. No, so this is more like the Intel syntax. Okay, so this is the AT&T syntax. You always follow that rule: base, index, size. Yeah. Right. So constant number here. I'm not 100% sure. I think I cannot say the size to be already. Maybe can maybe if the size of the data that you're moving is determined by like the suffix of number, then why do you have to specify it with it? That's a very good question. That's first of all, the parenthesis here means this is memory, not register. Right? So you need some kind of indicator for that. Then the size here may not be that important. For the Intel syntax, sometimes you don't have that. You don't have this, let's say. So here you have a L or B. For the Intel syntax, you don't have to sometimes, because sometimes it's not ambiguous. But I will show you another example here. Sometimes it can be ambiguous, like this one, right? Do you have more questions before we move on? Okay. Pretty cool. What happened? I just managed it. For example, it could be an assignment. Let's say you have a second level, You can have an integer, int a, right? Then you may have a is a plus 2 assigned to a, right? So this a, this is an integer. This eventually will get its own memory address. So the compiler will reserve 4 bytes. Let's assume this is 4 bytes. The compiler will resume 4 bytes in the memory for this variable. Then you want to do some computation, adding something to this. You first may need to move this 4 bytes from the memory to the CPU. So that's a move instruction from memory to CPU. Then you will need to do a add instruction from the register and a constant, which is 2. Then you may want to move that back to the main memory. So you have another move instruction from register to main memory. Yeah. Cool. Okay. So there are some cases. What do you ask there? It could be a little bit ambiguous, like this one. We are moving a constant number 2, just 2, value 2, to EBX, the memory address EBX. Okay. So EBX is 4 bytes, right? But that's the address. It points to somewhere in the memory. What it points to, it could be 1 byte, 2 bytes, 4 bytes, right? Then we're trying to move a number 2 here. Then how big is this 2? It's not clear, right? So this is a very small number. It can be represented just using 1 byte, and you can also represent it using 8 bytes. So this instruction is actually very ambiguous. You're not sure how many bytes you are moving to here, right? So that's why a more accurate version of this instruction. So if you do something like this at assembly level, you may get a warning. Then the assembler may choose the default choice. If you want to be more specific, you can use move B, which means byte. Then you are just moving 1 byte. You can move a W, a word, 2 bytes, or you can move L long 4 bytes, right? So depending on if this is little endian or big endian, those 3 instructions are going to move that 1 byte to different address. Make sense? Because how you store that is different. Yeah. So those are the move instructions. We saw that already. There are some other move instructions. They do not have the name of move, especially some with stack operations. So how many of you already know what stack is? Okay, so some of you know, not everyone. So stack is a data structure that first in, last out. You add something to stack first, then it will come out last. So stack, there are 2 operations associated with a stack. One is called push, another is called pop. So push, where put something on the top of the stack, and the pop will pop that top of the stack to somewhere else. So this is a very complicated operation here. Let's say we have an instruction push EAX, %sign EAX. So we know, so this operation instruction is always associated with the memory. It's going to push something onto the stack, and the stack is in the memory. And where the stack is actually specified by the register ESP. Okay. So ESP. So even though the name of this instruction, when you look at this instruction, you do not see ESP appear in any part of this instruction, but it's implicit there. When you push something, you are going to push that where ESP at. So when you push %EAX, you are putting the value of EAX onto the stack, and you are not changing the value of EAX. Then the operation is called pop. Then you can pop EDI, then you are popping something from the top of the stack to the register EDI. We can talk about this later when we see concrete examples of those instructions. Like I said, we use this a lot in our hacking class. load the effective address, we can skip that one. Then we have arithmetic and logic instructions doing math operations, basically. Add something, you can add one word and 1 byte, and B, you can subtract something, you can decrement something, you can multiply something, you can shift something, right? So those are the basic operations the CPU provides. The add operation can be super fast. Subtract can also be super fast. Multiply can be very slow, especially this one. You multiply something from the memory to a register, it will be very slow. Multiply itself is very slow. So multiply eventually can be translated into multiple additions, right? That's why some optimizations, they will try to use more additions instead of multiply. So that's the second class of instructions, the computations. The first one is move. The second is computation. The third one is control flow instructions. So if you have a sequence of instructions, if in that sequence of instructions, you do not have any of those control flow instructions, so what the CPU will do is execute one instruction after the previous one. You will just keep going to the next instruction, right? But I talked about the cases like in Java, in Python, when you program, there are branches. You use a predicate. So how do you implement that at the CPU level? Then you use jump instructions or even call instruction if you want to call a function. So the jump instruction, you can use a label there. So label is a concept in the assembly language. It doesn't exist anymore in the disassembly, in the binary code. It just becomes an address. So the jump somewhere, then you are directly jumping to some place. Okay. There is no question asked. You just the CPU is not going to compare anything. The CPU is unconditionally jumping to some place and keep executing from that place. This is called a direct jump because even though at the assembly level it's a label, after you compile, it becomes hard-coded address. After you compile the code, it becomes hard-coded address. So the instruction here, this part is hard-coded. Then you can also have something like this, jump to a register, to a register name. So you are jumping to the value which is inside the register. And obviously, that's not something you can predetermine, right? So the address is only determined when you are about to execute this instruction. Then you look at that register, that's where I'm going. Okay, that's where I'm going to execute next. So this kind of instructions are called indirect jumps. In security, we have a lot of issues with those. That's why a lot of our research we are doing is to secure those kind of instructions. There are jumps. There are also conditional jump. So this one is unconditional jump. It's just a JMP. Then we have conditional jumps. It starts with J. Then after that, the name has different conditions. Then you can have a label. You can also have a register. So let's say JE, E here means equal. NE means not equal. So before this instruction, there must be somewhere, there must be a comparison. The CPU is comparing two numbers. If they are the same, we are going to take this jump. Otherwise, we do not take the jump. Do not take the jump means we're going to execute the next instruction after JE. But there is also JNE. JZ means if the 0 are greater, G means greater, GE greater or equal, L means less or equal. So those are unconditional jumps. Obviously, you don't have to remember all those instructions. If you say an instruction and you don't know what it is, you just Google it or ask a large language model. So they give you good explanations. So here is one example. So we have a CMP. This is a compare instruction. This instruction takes two operands. The first one is source. The second one is destination. But in this case, we're not going to move anything to the destination. We're going to compare those two. Okay. So what the CPU does is to subtract one of them from another, then update the E flag registers we talked about. It will update the 0 flag, the sign flag, the carry flag. It will update those flags. Then the next instruction, JLE, jump less equal, will decide whether we should take this jump or not, depending on the combination of those bits. Okay. So this is the compare instruction. Another very important instruction I want to talk about is the call instruction. So this directly maps to the function call in the source code. Let's say here we have a function. We have a function too small. So we have a main function, right? In the main function, we call printf, right? So this is what we saw last week. In printf, we print out the hello computer science, right? Computer system, whatever. So the main function is the entry point as a C programmer you develop. Especially as an application level C programmer, you always start with the main function. That's your entry point. That's because most of the C programs are compiled and linked with the standard C library. And the standard C library has a function called, I believe it's called the libc start main or something. I think it's called like this. Libc start main. Yeah, so this function. So this is a C library function developed by C library developers. And this function will eventually call a function called main. Okay, and this is what you develop as a C developer. And when you develop a main function, you already make sure the C library eventually will call your function. So that's the C standard. But if you are an operating system developer, your OS is not going to link against the C standard library. The OS doesn't have a C standard library. So you don't really have a main function. But if you look at the Linux kernel code, they do not start with the main function. So any function call, including that printf or call to the main, eventually will be, and this architecture will compile into the instruction call main. So the main here will just be a hard-coded address. Eventually, it will become something like this. And call is the instruction. So this instruction is complicated. It does two things, basically two things. The first one, it will push. The push is the instruction we just talked about. It will push the current code location, actually the next. So after the main function, there will be some other instructions, right? Let's say the main function is at address 1111. Then there may be another instruction at address 1113. Let's say this is 2 bytes. Okay. So after the main function, if you finish, the CPU finish executing the main function, what happens? You have been programming Java. This is a function. After calling that function, what happens? You returns, but returns means inside of this function, right? So what actually means is the program will keep executing whatever is after this main function, right? Then how the CPU knows that after executing main function, it should execute the instruction after the main function. How can the CPU know that? So what this instruction does is to push the address of the next instruction of the main function, okay, to the stack. So it stores it somewhere. Then in the function main, eventually at the end, there is a return instruction, and the return instruction is going to pop the top of the stack to the special register P6 or EIP. So the CPU will keep executing from there. So the call instruction does two things. First is push the next instruction, the address after the function you are calling, to the stack. And the stack is pointed by the register ESP. Then it performs an unconditional jump to the function you are calling. So just those two simple operations. Then in that function, in the main function, or any other function that I'm developing, there at the end, there will be a return. If that function has multiple branches, most of the functions are complicated enough to have multiple branches. Each branch at the end, there should be a return instruction. Okay. And this return instruction also do something very simple. It will plot whatever that ESP register points to, which is in memory, which is in stack, and it's supposed to be an address there. Okay, supposed to be the return address. We're going to move that return address from the memory to the register EIP or PC. Then the computer will keep executing at where it was interrupted. Okay, that's a basic idea. Okay, so a lot of the security issues here, for example, memory can be overwritten, and you are storing a very important information where the CPU later should be executing in a memory location. So why would attacker overwrite that memory? Right. So that's what we do in the software security test. So stack, I guess we can skip a little bit, then we talk about it later. This one we can skip for now, save it for the next week. So how much time do we have? 20 minutes? So the class will be, when did we start? 11:45. Yeah, we only have like 20 minutes. Yeah, okay. So probably I do not have time to save for you guys for the assignment, but we need to look at this. So this is the very first piece of code of the operating system we are going to study this semester. So this is the x86, and this is the boot asm.s. So this is a very first piece of code of this operating system executed on the x86 CPU. Okay. So a little bit context here. We do not need to understand everything here today. Okay, we do not even need to understand the big picture here. Why we are doing this? That's complicated. What our goal today is just looking at each instruction, each assembly instruction, and try to understand what each instruction is doing instead of thinking about why we're doing it. Okay, so this happens right after you press the start button of your computer. After you press that, there will be some code executing. That code will be in something called BIOS. For PC, there is a device called BIOS. For modern PCs, I don't think it's called BIOS anymore, but for your laptop, for your phone's tablet, for ARM architecture, you don't really have something called BIOS. But for PC, we have something. The BIOS already have some code there. The code will do something. Okay. So what that code, we didn't program that code. Even OS developers, they didn't program the code. BIOS developers program that code. So that code will get the first sector of your disk storage and load that to a specific address in the memory. Physical address. We don't have virtual address yet. So this piece of code is the code in that first sector of that hard disk. Okay. So this is part of our OS. And the BIOS will load this piece of code to a specific memory location, which I think they put it somewhere. It will actually load this at the physical address CC00 with CS number 0. So actually it will be CC000. I think that's a physical address, but it doesn't really matter here. Okay. Then the CPU start executing from here. And right now, the CPU is something called the real mode. The x86, the x86 CPU starts running something called the real mode, which is 16-bit, not 32-bit yet, because it's backward compatible with early CPUs. So only after 2 or 3 86, it has something called the protected mode when we have 32-bit. So that's why here in the assembly we have a directive .code 16, means the rest piece of code should be compiled into 16-bit of code, not 32-bit of code. Okay. Then we have a label here, start. I just give it a name. This is the start. So this all of this, they're not going to compile into in any instruction. The very first instruction is this one, CLI. This one is clear interrupt. Means we're going to stop interrupt on this machine because we haven't set up interrupt handler yet. So now if some peripheral, it's a camera, a microphone, sending a hard disk, send out an interrupt, we do not have code to handle that. We will simply crash, right? So we disable the interrupt first. Then we're going to do some operations. So look at those instructions. So those are the instructions we already started today. The first one is XOR. This is exclusive OR, okay? W means a word, 2 bytes. We're going to do an exclusive OR on the register AX and AX. So what we are doing here? What if we are doing exclusive OR with two same numbers? Would that make yes, we're just doing 0. So we're basically setting 0 to the register EX. There are other ways to do it. We can do a move 0 to that, but that instruction may be longer than that. If we move 0 EX, that may take 3 bytes, but this one may only take 1 byte. That's why we're doing this. Then we are copying or moving from EAX to DS. So we know that AX has 0, then we are setting DS as 0. We are moving AX to ES, SS. So we are setting DS, ES, CS, or SS or 0. So we're basically setting up some system registers there. Then after that, we have another label, okay? Then we have a in. So B here means byte. In is another instruction. This instruction is reading something from I/O port. So we're reading from peripheral or I/O. So this is also something special on the x86 architecture. For your phones, your ARM architecture, everything is memory mapped. So you do not have an instruction like this. So if on those architectures, if you want to reading from a port, reading from a peripheral, you just use a move instruction, like what we did here. Okay. So it's called memory mapped I/O. So basically you put I/O into memory address. Then you can use the same instruction as regular memory operations. But here we don't have that. So we have the in instruction. So we are going to read. So the first one is the source, right? The second one is the destination. So the destination is a register, the register AL, 8 bytes. The source is a specific number, the constant. So we are reading from port number 64. We are reading 1 byte to AL. That's it. Okay. And that port number is a different concept from the TCP port number. Okay. We're talking about I/O port number. Then we're going to do a test. This is similar to compare what we saw before. We're going to test is to subtract something from another. A test is to do an exclusive OR on those two things actually. So we're going to test if the value in AL, which we read from this port, is number 2. If it's jump not 0, which means if it's not number 2, what will happen here? So we talk about this instruction, JNZ. N is not, Z is 0. Jump not 0. So when it's not 0, where are we jumping to? We're jumping to a label, right? And this is the label here. So what is this piece of code? Those 3 instructions. Yeah. It's actually a loop, right? We're just reading from that port to say if the port is giving us the number we're looking for. If it's not, we just keep reading it. Yeah. So we're waiting for some device to get ready or to, I don't remember which one this is, but we're basically waiting for some device to get ready so we can move forward. Okay. Then after that, when that device is into a state we expect, then we're going to move this. We're going to move 1 byte EI to the register AL again. Then we're going to out. We're going to out the value AL to the port number 64. So when that device is at a state we expect, we are going to send 1 byte, which is DI in hex, to that port. So we're telling the device to do something. Okay. That's it. Then we have another loop here. That's something similar. And this time we are setting a different port number. So you may ask, what is that port number? So for something like this, you need to go to the CPU document, you need to go to the hardware document, figure out where they are. Okay. So I believe that it's somehow related to the keyboard. And also, oh, this one is related to enabling the address 20 line. There is a particular line in early Intel CPU, it's address 20, and it has to be explicitly enabled, I remember. Yeah. So after that, we are going to switch to the 32-bit version. So we are actually getting ready to switch to 32-bit. So 32-bit version, first of all, there is a register CR0. We talked about that. There is 1 bit in that register to indicate we are in the real mode, 64-bit, 16-bit, or protected mode, 32-bit. We need to enable that bit. Okay? But before we enable that bit, we need to set up the environment. So when we enter that 32-bit, the CPU where the program will not crash. So what we're doing here is we're going to load the description table. So this is a special instruction for that. So those instructions are privileged instructions. You can only execute as a kernel for OS mode. Then a simple move, a simple OR. So OR here is basically just a set some bit. Some bit, it was 0 before, but we are setting was 1, right? So setting a bit, and we're not changing other bit. For example, here we're only setting 1 bit for PE. And this one is just a constant since we're on the $sign, right? So this is a hard-coded constant, and we're setting maybe 1 bit there. And we're going to move whatever we set to the register R0. Then we are entering into the real mode. So after real mode, we need to do a jump to our new 32-bit code. Previously it was code 16, now it's code 32. So from here, the code is 32-bit. Previously it was 64-bit. And obviously we want to start writing 32-bit code as soon as possible. That's why previously we only looked maybe 10, 15 instructions. Here, this is actually a jump, right? JMP. But this is an air jump, this is a long jump. So the previous jump we look at is what we call a near jump. It will only change the EIP. This long jump will not only change EIP, it will also change the CS register, the code segment register. Because before that, we're still using segmentation. So you don't have to understand every bit of this, just to try to understand each instruction here. Okay. Then after that, we are setting up those system registers again, ES, SS. We are setting a specific value to those registers, right? Also, we are setting FS and GS, and we are setting them to 0. So because we move 0 to AX, then we move AX to FX. So you may ask, why do not we move 0 directly to FX? It's possible that we don't have an instruction to do that. Okay, we probably need to test if we probably don't have an instruction to move 0 to FS. We have to do a general register to FS. Okay. Then we set up the stack pointer. Now we have stack. We're moving some address to the stack pointer. Now we have a stack. As soon as we have a stack, we can use say functions. That's why we have a call to boot main. Okay. So this is the very first say function of this OS. Because the boot main function, this is a function, and the function will have a lot of stack operations at the beginning and the end of the function. So if you do not set up the stack before that, your program will crash eventually. That's why for this kind of architecture, you have to write, maybe we have like 30 lines or 20 lines of assembly code. You have to. Before you have your first say code there running, you have to run at least have assembly code to set up the stack. For some other architectures, like ARM I work with, they have some special design to, there is a hard-coded place address where you can put a hard-coded address for your stack. And that is directly loaded to the register, something like ESP when your system boots, which means you don't have to write even single line of assembly code. You can just press single. So the requirement here for any C code to run is you have to set up the stack. So after that, we are going to boot main. So we're not going to execute here. Okay? The boot main is not supposed to return. Okay, this function is not supposed to return. This thing, we're eventually starting the whole OS, and on top of OS, you run many different applications. So if something is wrong, if something returns, then there should be an error. And what this piece of code doing is trying to report that error. If it ever executes here, this piece of code will report, in a undefined state. And then there is this is an infinite loop. So this is one instruction. This instruction is labeled as spin. So that's basically address. And this instruction is jumping to itself, right? So we're not doing anything here. We're just doing an infinite loop here. So that's, so then we have some data there. So that's the very first piece of code of this operating system. And 30 lines of instructions. And you don't have to understand the bigger picture yet. There will be a module. We're going to talk about each of them. But what I want you to understand is each instruction. Now you should be able to understand that. Cool. Any questions? No. Yeah. So the system we are using actually is in front of you. So for example, we're talking about general, there are multiple layers of the filter. There will be something different. So the kit of the environment, there were a lot of people binary, and those actually memory and data control that piece of binary. And it could be multiple stages. There are more, sometimes 3 stages. So in the system where you don't have everything you want to do. Okay, I guess see you guys Thursday. Thank you. Yes.
So there be a new slide for this, so, or,
Yeah, I will add something. I haven't finished the slide.
because I was wrong, if it's possible for me to like get the slide before, so I could like read it a little bit first.
I will try to do that, but I cannot promise. This is the first time.
Okay. Oh, okay. I see. And
Yes, yes.
I had a question about GitHub. I had a question about GitHub Classroom.
Yeah.
I think it would work. I'm sending in
Okay.
Northeastern email. Like, not even log into GitHub Classroom.
Hey, how are you?
So maybe I can.
Yeah, that's great.
Yeah,
I remember.
So you were.
How's it, which class is this, Victor?
What I need to
Yeah?
check is if you.
The fun?
Yes.
Yes.
My second class. Yeah, you can't tell so early, right?
What are you teaching?
Don't remember.
What was that?
What are you teaching?
Now this is DS 4400, so machine learning 1.
Wait, so you're teaching machine learning one?
Yeah.
Are you teaching next?
Not next semester. Yeah, it's all right. But I feel, maybe next fall.
So Professor Wu was teaching it, and then you're teaching it.
Yeah, usually
You're professing.
we just kind of move around so that nobody has a course for like too long because they're, yeah.
You're teaching practical.
Not machine learning 1. Yeah, I'm not gonna do Are you asking if I'm teaching neural networks?
Yeah.
No, not an ML1. We have like a whole
So
course
our-
dedicated to it.
Currency issue
Yeah.
of, you know,
Basically,
when you make that, you can like create a repo for you and everything.
Our goal.
And you are
Yeah.
supposed to get everything first. So you can.
Yeah, is it coming? Is it good? Or do you feel like your discrete is,
So
how'd I do? Set you up for algo is my question.
What I can do is
Pretty
you
good.
can
Yeah, you feeling ready?
send me an email.
Still low is the wrong reduction.
Then I will
Yeah.
check under,
Yeah, I don't really.
in our repos. Oh, you're teaching?
Hi, yeah, I'm teaching. I'm
Sorry,
sitting up.
sorry.
Oh, no problem at all. I'm recommending, I taught discrete last, and now I'm seeing all my students here.
Oh, really?
Yeah. I don't know if we've met yet. You must be in the department.
Yeah.
Matt,
Jimmy,
Jimmy, nice to meet you,
nice to
Jimmy.
meet you. What are you teaching?
Machine learning one now.
Oh, machine learning one.
Yeah, 4400.
So I will log off here.
Yeah.
Yeah, I teach, this is computer system.
Yeah. Cool.
Yeah.